Okay. Actually, I'm gonna start with just this window. So the plan for today, no quote of the day today. We're just gonna jump right into it. The plan for today is to finish up chapter 7. We had one example from last time that I just want to finish up on confidence interval for standard deviation of variance. The bootstrapping section I'll leave as a supplemental lecture. I'll post that to YouTube. Probably have that up later today. Sorry, my allergies are bothering me. I don't know what it is, but in the morning, like when I'm just sitting here, my allergies don't bother me. And as soon as I start talking, my allergies start bothering me for a little while. So, but anyway, so the bootstrapping lecture, I'll post that to the YouTube playlist, and you can watch that, at your leisure. And that'll be section 7.4 to finish out confidence intervals. And then today we're going to start into chapter 8. So the last really big topic of the course, hypothesis testing. We'll get started on that today. I mentioned last week that it would be a good idea to kind of read through the first couple of sections of chapter 8 just to get an idea of how hypothesis testing works, what the goal is, and so on. And really the main thrust of today will be to kind of understand that background of hypothesis testing. What is the goal? What is the logic behind it? We're not really going to be, in most of chapter 8, introducing any new math. It's really going to be applying the same math that we've been using in chapter 6 or in confidence intervals, but applying it to a new area of inferential statistics hypothesis testing. So that's really the challenge in chapter 8, is not really the new calculations, but what calculations are we doing at what point, and why are we doing those calculations there? Okay, so recall that our confidence interval for the variance, our upper and lower bounds look like n-1 times s squared, the point estimate for the variance, over a chi-squared number. And chi-squared was that distribution that we talked about that was kind of right skewed. We have a chi-squared right number and a chi-squared left number. The chi-squared right is the larger number, so since it's in the denominator, it's associated with the lower bound. The larger number in the bottom makes the fraction smaller, and vice versa. Degrees of freedom are n-1, and we had our chi-squared table that we can use to look up our chi-squared critical values or our chi-squared indices. Okay, so let's start on this problem. So here we have an example where a company produces a certain type of cookie. The machine that produces the cookies is calibrated to produce packages with a mean weight of 32 ounces and a variance of 0.015 square ounces. Since this is the variance, it's in square units. And we want to compute a 95% confidence interval for sigma squared, the variance, on the basis of this given sample. Sample size 25, and the sample variance is 0.029. So it's the sample variance 0.029 is not right on 0.015, which is what we would hope. But kind of our question is, okay, well, is this sample variance so far away from the variance that we'd expect, 0.015, that we think something has gone wrong with our process, with the machine, something like that, and we want to shut down the production line and maybe recalibrate the machine or investigate what has gone wrong. Obviously, that's a costly process, so we don't want to do that for no good reason. So if we think that this deviation was just due to sampling error, we wouldn't do that. If we think that it's too big to only be due to sampling error and there's something systematic underlying this difference, then we will shut down the process, we'll investigate, we'll recalibrate, whatever we need to do. So that's kind of the question we're trying to answer here. And again, like I mentioned last time, questions like this kind of touch on hypothesis testing. So we're bridging the gap a little bit here. But we have a confidence interval question and then kind of an interpretation of that confidence interval, something that's a little closer to hypothesis testing. Okay, so I have a sample of size 25, sample variance 0.029, and let's also assume normality. If we don't assume normality, we really can't go very far here. So we'll assume normality. And I see my confidence interval looks like n minus 1 s squared over a chi-squared number. So let me start by finding my two chi-squared numbers. Remember, chi-squared starts at 0, 0, and has this kind of right-skewed shape. That's my chi-squared distribution. I have two numbers, chi-squared left and chi-squared right. I want a 95% confidence interval, so 95% area in the middle, which puts 5% combined between the two tails. I don't have super nice symmetry between the indices because everything's to the right of 0. But I can impose that symmetry in the sense that I want the area in the left tail to be the same as the area in the right tail. So 5 total percent left over. That puts 2.5% to the left of chi-squared left and 2.5% to the right of chi-squared right. Okay, let me switch my share here. And remember, this was our chi-squared table. Our chi-squared table gives us areas to the right, so areas in the right tail. We have a list of some different areas here, along with some degrees of freedom. So the degrees of freedom column tells us which chi-squared distribution we're on. Different degrees of freedom will give us slightly different distributions. And then we look for the appropriate degrees of freedom with the appropriate area to the right. And that gives us a chi-squared index in the middle. So this table works kind of backwards of the way the standard normal table works, or it works in a similar way as to how the t-table works. So I need areas to the right, and I see the area to the right of chi-squared right is just 2.5%. That's not too bad. The area to the right of chi-squared left, well, chi-squared left has 2.5% area to the left, 97.5% area to the right. So these are my two areas to the right that I need to look up on my chi-squared table. And I know my degrees of freedom is n minus 1, or 25 minus 1 is 24. So I need 24 degrees of freedom and then 97.5 and 2.5% areas to the right. So if I keep scrolling down to 24, I can't quite see the top column, but I do note that 97.5% area to the right is the middle of the left half of the table. And if I look at where that column intersects 24 degrees of freedom, that is right here at 12.401. 12.401 is the chi-squared index with 97.5% area to the right. And then I want to do the same thing for chi-squared right. 2.5% area to the right, 24 degrees of freedom. 2.5% area to the right means we're in this column. And then we're looking for 24 degrees of freedom going across. And that looks like the correct line. And that gives me a chi-squared index of 39.364. And the good news is at this point, we really have completed the hardest part of the problem. Now we just have to plug everything into our bounds up here. So my lower bound and my upper bound both look like n minus 1 s squared. So n minus 1, 25 minus 1 is 24. times s squared. Note that I'm given s squared directly here. I don't square this number. I just put in 0.029. And then over a chi-squared number. Again, the bigger chi-squared number goes in the bottom of my lower bound. So this is 39.364. And again, remember, we looked up this number off the chi-squared table. We don't additionally square this. So this symbol here, this say chi-squared left or chi-squared right, already takes into account the squaring whenever we look up this number. Remember, we got the chi-squared numbers by taking standard normals, squaring them, then adding them together. That's where that squared comes into play. It's already taken into account, in a sense, in this number 39 or this number 12. So this 39.364, that's what goes in the denominator just as it is. And 12.401, the smaller number in the denominator of the upper bound. All right, so for our lower bound, we have 24 times 0.029 over 39.364. And that gives me 0.01, let's say 0.018. And my upper bound, the same thing. So I'll just hit second enter, but with a different chi-squared number. 12.401 in the denominator. And that gives me 0.056. So my 95% confidence interval for the variance is 0.018 to 0.056. So note that we actually didn't use this 32 ounces or even really this 0.015 square ounces at all. We also didn't use the sample mean at all. All that we used was the sample size, the sample variance, and then our confidence level. Now, our process control criterion is that if either the upper or lower bound are outside of the range 0.08 to 0.030, then we shut down the machine to recalibrate. We see that 0.018, the lower bound, is in this range, so that's good. But the upper bound 0.056 is larger than 0.030. So since this is outside the limits, we'll choose to shut down the production line, investigate, recalibrate, whatever we need to do to bring the process back under control. We think that something systematic has gone wrong and that this is more than just some sampling error that's leading to this deviation here, this high sample variance that we got from this sample size 25. So this is the kind of thing a manufacturing company would regularly do, not necessarily exactly this choice for how they would set up their controls for the process, but they would regularly take samples, they would run statistics on them, they would figure out, do I think that my assembly line is working the way that I think that it should, that I set it up to work, or do I think that something is out of control and that I want to shut things down, I want to investigate, I want to recalibrate, get things back under control before I start producing more products. Any questions on Chapter 7 confidence intervals? We talked about confidence intervals for mu, for the mean, whenever we know or don't know the standard deviation, confidence interval for p, the proportion or the probability of an event, and confidence interval for variance and standard deviation. Any questions on those? All right, and like I mentioned, the bootstrapping supplemental lecture we posted to YouTube. It actually, I have a supplemental lecture from a previous semester that's already on YouTube, so I'll probably just, pop that one in our playlist and then call it good. So I think that one should be fine for this semester as well. All right, so on to chapter 8, hypothesis testing. Let me switch my share and then just give me 1 second here. Okay, so chapter 8, hypothesis testing, like I kind of mentioned, the real challenge of hypothesis testing isn't so much the calculations. They're pretty much the same calculations we've done in confidence intervals and in chapter 6 with things like central limit theorem. Really, the difficulty is the analysis and interpretation side of things. So I want to start with a little narrative. This is what I think is probably the best explanation of confidence intervals I've seen. It's a little hard to read. It's scanned from an old stats book. The stats book is Statistics. The author is Friedman, F-R-E-D-M-A-N, published in 1980. So quite an old book at this point. But like I said, I think this is the best way to kind of understand this at an intuitive level before we get into all of the details of the calculation. So I'll actually read it because I know that especially on a small screen, it's going to be kind of hard to read and it's a scan and it doesn't look all that great. So I'll read it to you. But if you can see it fine and you want to read it yourself, feel free to like mute me and read it yourself or something. But I want to go through this. It's about 2 pages. It's 2 half pages and 1 full page. And I think that it's a really helpful exercise to go through this and just kind of get a feel for what's going on in hypothesis testing. Okay, so it says introduction. Was it just due to chance or something else? Statisticians have invented, quote, tests of significance to deal with this sort of question, or hypothesis tests, as we call them in this course. These tests are among the statistical techniques most widely used in the social sciences, and that's true. If you open up any medical journal, pretty much any finance or economics journal, you're going to see hypothesis tests all over the place. They're going to talk about p-values and statistical significance and all of that. In fact, it's almost impossible to read a research article in the social sciences or medicine or business or anything without running across them. Therefore, it's a good idea to find out what they mean. As Montaigne suggests, the main difficulty is in the language. Here's a passage which exemplifies the problem. So the passage they give is something that you might see in one of these research articles, and it says, with a one-tailed z-test, the null hypothesis was rejected at the 5% level. The difference must be regarded as statistically significant. So, of course, this is a fairly esoteric couple of sentences. And it says that the object in these next couple of chapters is to explain the ideas behind tests of significance and some of the language. Some limitations will be pointed out, and we're going to go through an example here. So the example starts here. Many companies are experimenting with, quote, flex time, allowing employees to choose their schedules within broad limits set by management. You can bring that into today's world by maybe saying remote work. But among other benefits, flex time is supposed to reduce absenteeism. Of course, a firm with many thousands of employees might have a hard time studying them, except on a sample basis. Suppose one firm knows that in each of the past few years, employees have averaged 6.3 days off from work apart from vacations. This year, the firm introduces flex time. Management chooses a simple random sample of 100 employees to follow in detail over the year. At the end of the year, these sample employees are found to have averaged only 5.4 days off work. The personnel committee is now meeting to assess this result. And we have a narrative here between 2 folks, the, quote, investigator and the, quote, chance skeptic. So the investigator says, among other benefits, flex time reduced absenteeism. On the average, days off work dropped from 6.3 to 5.4 this year. The chance skeptic says, now look, your sample only amounted to 100 employees out of 5,000 at the plant. By the luck of the draw, you just happen to get too many hard workers in your sample. All you're showing us is chance variation. Basically, all you're showing us is sampling error. The investigator says not true. The chance skeptic says, what was the standard deviation of your sample? Investigator, days off average 5.4 with a standard deviation of about 3 days. Chance skeptic says, well, the difference between 6.3 and 5.4 days is a lot less than one standard deviation. It's about, say, a third of a standard deviation. To me, that looks like chance variation, right? Getting a 1/3 of a standard deviation event wouldn't be surprising at all. So the investigator says, okay, I want to make a calculation, and for that I need a box model, kind of like a sample space kind of model from back in chapter 4. There are 5,000 tickets in the box, one for each employee, showing the number of days taken off work this year. We drew 100 tickets at random from the box for our sample. What we really know for sure is these 100 tickets. Agreed? So chance skeptic agrees. Investigator says what we're arguing about is the average of the 5,000 numbers in the box. You say it's still 6.3 days, and I say that it's gone down. The chance skeptic says, right, correct. What I say is that by the luck of the draw, you got too many small numbers in your sample. The investigator says, I understand. One more thing. We don't know the standard deviation of the box, but can we agree to estimate it by the standard deviation of the sample, 3 days? The chance skeptic says that sounds fine. So the investigator says, okay, now the standard error for the sum of 100 draws from the box is root 100 times 3 equals 30 days, or their standard error for their average is 30 over 100 equals 0.3 days. So suppose that you're right, suppose the chance skeptic is right, and the average of the box is still 6.3 days, then you have to expect the average of the sample to be around 6.3 days. And 6.3 to 5.4 is about 3 standard errors, because 5.4 minus 6.3 over 0.3 is -3. So note the detail here. We're not talking about the standard deviation of an individual draw, which was 3 days. We're talking about the standard error, the standard deviation of X bar, which is 3 over root 100, or 0.3 days. So that's the first important thing to note here. We're not talking about the standard deviation of an individual. We're talking about the standard deviation of X bar, because that's our estimator. So just an interjection there. And the chance skeptic says, I guess, I don't know. The investigator says, we have enough draws here so that we can use the normal approximation of the probability. The area to the left of -3 under the normal curve is about 0.1%. And he says, now you have a hard choice to make. And this is really the crux of the interpretation here, this next paragraph or two, where the investigator says you have a hard choice to make. Either you can say the average of the box is still 6.3 days, that the average has not changed, even in light of this flex time, or you can agree that the average of the box went down. If you stick with the 6.3 days, you need a minor miracle to explain the data, the sample mean of 5.4 that would happen less than 1 in 1,000 times. And the chance skeptic then says, what do you think the average of the box is? The investigator says, I estimate it as 5.4 plus or minus 0.3 days. We could say plus or minus 2 times 0.3 days or something, whatever. We have a small reduction in days off work here, but a real one. So this 5.4 plus or minus 0.3 looks an awful lot like a confidence interval. So basically saying that I have some confidence interval, he's going plus or minus 1 standard deviation. We might, for say a 95% confidence interval, go more like plus or minus 2 standard deviations, 2 standard errors, sorry. But nevertheless, that confidence interval does not include 6.3. So his argument is you can't just dismiss it as chance variation, because to argue that it was just chance variation or sampling error, you'd need a 1 in 1,000 type of event. It's so unlikely to just be due to sampling error that it seems there's something systematic at play here. The chance skeptic then asks, okay, does this prove that flex time reduces absenteeism? Maybe you've given an argument that absenteeism is reduced, but does this prove that flex time is what caused that? And the investigator says, no, we haven't proved that the change in flex time is what caused the reduction in absenteeism. We just proved, or we just really more accurately provided evidence or demonstrated statistically that absenteeism really went down. It wasn't just the luck of the draw. But if we wanted to prove that flex time reduces absenteeism, we might have to do something a little more detailed. We might have to set up two cohorts and give one of them flex time and the other one not flex time, randomly assigned, and see if the flex time folks, if their absenteeism goes down while the control group, it doesn't. That would be fairly difficult to implement, because if you have two people in the same office, one gets flex time and one doesn't, there's probably going to be all kinds of complaints about that, right? But anyway, in theory, like you could set up an experimental trial and do a bit more here, but we have provided statistically significant evidence that absenteeism did decrease, that the mean number of days off did reduce below 6.3 days. We haven't provided statistically significant evidence that it's like exactly equal to 5.4 or something. We've provided evidence that it's below 6.3 days. And really the crux is right here. I can't select it. It's because it's in OneNote, not in Adobe. But the crux is really right here. This idea that to explain this by sampling error would require it to be something that happens 1 in 1,000 times. So you either need a minor miracle to you can dig in your heels and say the status quo is still the same, the mean is still 6.3 days, but then you're saying that to explain the data that we actually achieved, this mean of 5.4, you have to have a minor miracle to explain that. The other approach you could take is to say, okay, my old worldview, the 6.3 days mean, the data suggests that we should overturn that we should instead go with a different hypothesis, a competing hypothesis, that the mean is now less than 6.3 days. And that means that we don't have to have a minor miracle to explain our sample mean of 5.4 days. And again, what it does not say is that the flex time is what reduced the absenteeism. We've argued that absenteeism went down, but the causative side of things has not been established. Okay. So I know that narrative takes a little time to get through, but I think it is a good way to kind of introduce the topic. And really the idea is, if we get sample evidence, empirical evidence from the real world that disagrees with our, let's say, status quo, our point of view of the world, we can either dig in our heels and say that sample just happened by sampling error, or we can change our worldview. And how extreme ought that sample be? How unlikely ought it be to get by sampling error before we change our worldview? And that's a question that we have to throw some numbers on that and basically make that part of the context of the problem statement. So there's not a mathematical answer to how extreme should that be before we switch worldviews. That's a number that we have to choose in advance. And then once we choose that number, the rest of it is just mathematics. Okay, so let's take another example here. So again, still not getting into the math, still just kind of discussing the logic behind the scenes here a bit, but we're getting kind of one step more technical. So we're going to get a little more technical and a little more technical, and then introduce the mathematics. So one of the probably most common examples used for hypothesis tests is this analogy to a jury trial. So if somebody is accused of a crime, they stand accused of some crime and they go on trial, and the jury can either find them guilty or innocent, but they don't really find you innocent. They kind of find you not guilty. So these are the two possibilities. So a person in reality could either be guilty or innocent. And the jury trial could decide that you are guilty or not guilty. Now, if the jury trial calls you guilty and you're actually guilty, that's a good result of the jury trial. It's accurate in that case. If it comes back not guilty and you're innocent, aka not guilty, that's also good. In these other two cases, we've made an error. If our trial calls somebody guilty, but they're actually innocent, we made an error. If our trial says that somebody's not guilty, but they are actually guilty, we've made an error. And these two errors have a trade-off, right? We can reduce one of them, but only if we're willing to make the other one larger. So if we're more draconian, if we take like a Cardassian standpoint from Star Trek, where you're arguing to prove your innocence in a trial, then kind of by default we would call people guilty. So we'd be calling lots of actually innocent people guilty, but we would miss very few of the actually guilty people. On the other hand, if we were very lenient, if we required an incredibly high standard of evidence to ever declare somebody guilty, we would miss a lot of the guilty people. We'd make a lot of errors where we're calling truly guilty people not guilty. We'd have a high error rate there, but we'd rarely convict an innocent person. We'd rarely declare a truly innocent person to be guilty. These errors face a trade-off like that. So we kind of have to decide, which side do we give the benefit of the doubt? Which error do I want to be smaller at the expense of the other error being larger? And at least in kind of the US justice system and the Western justice system, at least in theory, so we decide the benefit of the doubt is innocence. Right? So that famous saying, innocent until proven guilty. So by default, a person is innocent until we can provide enough evidence at trial to declare them guilty, to switch that mindset from saying, okay, I thought they were innocent, but now it's so much of a stretch based on the facts that have been established in the trial that I've got to change my worldview and go with the other hypothesis that they're guilty. Okay, so let's introduce a little bit of terminology here. We have hypotheses. These are statements that can be true about the real world. A hypothesis might be true or it might be false. So a hypothesis could be, I think this person is innocent, or I think this person is guilty. In hypothesis testing, we have two types of hypotheses. We have the null hypothesis. Typically, it's given the symbol H subscript 0. The null hypothesis is kind of the default hypothesis. In the absence of information to the contrary, we'll continue forward with this worldview, H naught, the null hypothesis. It's the default. It gets the benefit of the doubt. So if we kind of start with this default worldview, the null hypothesis, if we gather some empirical evidence, some sample from the real world, and it seems to be reasonably in line with the null hypothesis, we just continue on with that worldview. We're happy to do that. But what if the data that we get from the real world, what if the empirical evidence stands in contrast to the null hypothesis? It's discordant with the null hypothesis. It suggests the null hypothesis might not be correct. We have an alternative hypothesis. And I call this H subscript 1. And some books call it H subscript A with a little lowercase a. I think it's quite difficult to see the difference in a subscript between a 0 and an A, especially when I'm writing it and my writing is not super clear, or if you're reading it in small text. So I go with H sub 1, but you'll sometimes see it as H subscript A, the alternative hypothesis. If I have a null hypothesis, the kind of existing worldview, the default, the thing that gets the benefit of the doubt, but I collect a bunch of data, right? If I have my null hypothesis that the mean number of days off is 6.3, I collect a bunch of data and my sample mean is 5.4, and that's statistically speaking quite far below 6.3. I might say that that's enough evidence against the null and in favor of the alternative that the true mean has gone down, to say, okay, I'm not going to keep moving forward with the same worldview of the null. I'm not going to keep moving forward, digging in my heels and saying the mean is still 6.3, because the evidence is just suggesting that I need to revisit that. The evidence suggests that I should reject the null hypothesis and move forward under the alternative hypothesis that the mean has gone down, that the mean is lower than 6.3 in our narrative example. So the alternative hypothesis is the thing that we're trying to provide evidence in favor of. And remember that the null is the default. It gets the benefit of the doubt. So it's not just that we need to provide a bit of evidence in favor of the alternative and then we just switch right away, right? We're not flippant about this. We actually set a pretty high bar, right? I mean, in the jury trial example, it's the bar is beyond a reasonable doubt. We set a pretty high bar. We say, okay, I mean, if we collect some evidence and it looks just like the null hypothesis, we move forward with the null. But if we collect some evidence and it looks a little suspicious under the null, and it looks like it goes better with the alternative, we're still going to stick with the null. It's the default. It gets the benefit of the doubt. We have to collect evidence that really, really is discordant with the null hypothesis and works much, much better with the alternative hypothesis. That has to be really strong evidence in order for us to kind of switch sides, in order for us to reject the null in favor of the alternative. Same with a jury trial. What would our hypotheses be? Our null hypothesis is that the person is innocent or that they're not guilty. But here we'll stick with the wording innocent for the hypothesis, because the hypotheses are dealing with the real world situation. And the alternative is that they are guilty. So again, we give the default, we give the benefit of the doubt to the null hypothesis, to innocence. We run the trial where the evidence is presented. And we ask, is that evidence, I mean, if it's consistent with them being innocent, we keep them innocent. If the evidence doesn't look great for them, if it kind of looks like they're guilty, but we're not really sure, we declare them not guilty. We do not overturn the null in favor of the alternative unless we have a ton of evidence, unless there's a plethora of evidence where we can say that I'm convinced beyond a reasonable doubt that the person is guilty. Then we overturn the hypothesis of innocent. We reject the null in favor of the guilty hypothesis, right? We need to be convinced beyond a reasonable doubt. That's a very high bar. There needs to be a lot of evidence against the person, not just like preponderance of the evidence or something like we might have in a civil trial. But here we need, so it's not just like 51% sure the person's guilty and then we call them guilty, not like that. It's like we need to be something like 95% certain that they're guilty before we would switch our our point of view from calling them innocent to calling them guilty. We need to be quite sure they're guilty beyond a reasonable doubt. Okay, so if I look back over here at my chart, if I call a truly guilty person guilty, that's a success of the trial. If I call a truly innocent person not guilty in the trial, that's a success of the trial. Sometimes there will be a truly guilty person who we call not guilty. Maybe there is a bit of evidence that they're guilty, but not enough to overturn that very high bar. As kind of an aside, that's why we use the terminology not guilty. I might say, like, if I was a betting man, like, I think they're probably guilty, but I'm not super, super convinced. Right. So maybe I think there's more evidence they're guilty than they're innocent, but it doesn't meet that super high bar. So I would still declare them not guilty. Right. So a not guilty verdict doesn't mean that the jury has looked at the evidence and they're really certain the person is innocent. It just means that they're not really certain that the person is guilty. So that's why we use the terminology not guilty. But sometimes we declare a truly guilty person not guilty. Sometimes we should overturn the null in favor of the alternative, and we don't. And sometimes we declare a truly innocent person guilty. Sometimes we do overturn the null when we shouldn't have. So this is when we reject H naught, but H naught is true. When we reject the innocent hypothesis, even though the person is actually innocent. And this bottom left quadrant is when we do not reject H naught, or we fail to reject H naught, but H naught is false. A perfect test would always reject a truly false null and never reject a true null. But our tests aren't perfect, right? We can't drive both of these error rates to zero. If we push one down, the other one bumps up. So we have names for these. Rejecting a truly false null, we call that error rate alpha, the Greek letter alpha. And we call that a type 1 error, rejecting a true null. So this is our type 1 error. This other error here, we say that it has rate beta. And we call this a type 2 error. I mean, it would be super nice if alpha and beta could both be zero or really, really, really small. But again, if we push one down, the other one goes up. So there's a trade-off to be had here. In the US and kind of similar justice systems, at least in theory, we push alpha down. We say that it's really bad to declare a truly innocent person guilty. So we push the type 1 error rate down. And we understand that that trade-off means that we have a high type 2 error rate, that we more often let guilty people go free. We would rather let more guilty people go free than convict more innocent people. Again, that's not necessarily the perspective across all locations or across all times or across all sci-fi universes, but that is, the US justice system and similar justice systems have this this idea built into them, that we set a very high bar for declaring somebody guilty at trial in an effort to reduce the type 1 error rate. And the price we pay is that there are going to be lots of people who are guilty and who there's a pretty good amount of evidence against them, and it doesn't quite meet that high bar, that we think, yeah, they're probably guilty. I mean, some somewhat of a famous example in OJ Simpson. He died this past weekend or last week or something, right? I mean, I think, if you polled most people would say, yeah, we're pretty sure he's guilty, but at the jury trial, they weren't able to prove that beyond a reasonable doubt. So again, this analogy to a jury trial is a pretty good one. We have a null hypothesis of innocence, an alternative hypothesis of guilty. If the evidence that we collect is in line with the person being innocent, we continue forward believing they're innocent, or continue forward under the presumption they're innocent. If the evidence we collect kind of points to them being guilty but isn't super strong, we stick with the default. We stick with the null. We give it the benefit of the doubt. If it's not super strong evidence they're guilty, we declare them not guilty, they go free. In order to switch from our null to our alternative, we need to have a lot of evidence, very strong evidence, beyond a reasonable doubt that they're guilty. And at that point, we've got to say, okay, I mean, if I dig in my heels and say this person's innocent, that's just so discordant with reality that it's almost laughable that they would need a miracle. They would need to be the most unlucky person in the world to have all this evidence against them and still be innocent. I don't think that's likely to be the case. That's a really bad way to explain the evidence. So therefore, I will switch my worldview and declare them guilty. So this is the structure of hypothesis testing as well. We do some calculations. We say, if the person was innocent, if the null hypothesis was true, how unlikely would it be for such evidence to exist? If it would be extremely unlikely for such evidence to exist under the null, but also more likely under the alternative, then we reject the null and go with the alternative. If it wouldn't be all that unlikely under the null, even if it would be more likely under the alternative, but if it wouldn't be all that unlikely under the null, then we stick with the null. We fail to reject H naught. We move forward under the presumption that the null is still true. Okay. So that's really the tricky logic here. But if you bring it back to this jury trial, or if you think through that narrative again, I think it helps a lot. And that's why I'm spending so much time going through these examples over and over and pointing out these details. Okay, so a couple of notes down here. Give me 1 second real quick. Okay, so a couple of details down here. I just kind of wrote out much of what I just said, just to make sure that I don't forget anything. Yeah, one little piece of nomenclature: the power of the test is 1 minus beta, 1 minus the type 2 error rate. So that's a number that sometimes gets thrown around. Oh, and then yeah, so a good other point that I should mention is that back when we were talking about Bayes' theorem, we talked about medical testing, and we saw for things like screens, if we thought of a medical test, so it's a different example over here, a screen for a disease, where we just test everybody for the disease, right? Like, we don't particularly think this person has it based on symptoms or something. We're screening for it. So something like a mammogram, something like a can't think of the word, but GI scope, let's say. So for a screen for a disease, the null hypothesis is that no disease. The alternative is that they have the disease. And in this case, actually, to jump from the null to the alternative, for something like a medical screen, we actually don't require that much evidence, right? Because the cost of saying that your screen came back positive is usually just something like maybe an extra test, maybe it's a little bit more expensive, maybe it's a little more annoying or invasive. Maybe there's a couple of weeks of slight stress between when you get the positive screen and the negative follow-up test result. But compared to the cost of compared to the cost of a false negative, where we say, oh yeah, you don't have the disease, don't worry about it, and the disease progresses for another year or a couple of years before it's caught, that's a much higher cost usually for these types of things that are screened for. So in this case, we still have the same kind of hypothesis set up, but we wouldn't have this kind of like high bar to switch from the null to the alternative. It would be a much lower bar, because the cost of switching from the null to the alternative when we ought not have is much lower than the cost of digging in our heels and sticking with the null when we ought not have. So even though the setup and the structure is the same, the bar to switch from the null to the alternative is much lower. Okay, so in chapter 8, we're going to talk about 3 tests, 2 hypothesis tests for the mean and 1 for proportion. We won't talk about hypothesis tests for variance or standard deviation, although they're not super difficult to build up based on what we see from these 3 tests we'll cover and what we know from the chi-squared distribution with confidence intervals and so on. All right, so let's talk about the z-test for the mean. And we've gone through a lot of the kind of philosophical background of what hypothesis testing is. So we're going to actually jump right in, kind of dive right into the deep end. And we're actually just going to start working through this problem. I'm going to work through it. It's going to go a little bit slowly for this first problem, because we're going to kind of build out the technique, the mathematical side of the technique, as we're going along. So I'm going to do it slowly and carefully, and probably revisit important topics a couple of times. So this first time through, we'll go slowly. Not if you're doing a homework problem or on an exam or something like that, it's not going to take this long to go through a problem. We're just kind of building the technique through this problem. So that's why it's going to take a little while. This one problem will likely take us the rest of the class period today. But again, not every one of these problems is going to take 45 minutes. It's just that we're kind of building out the mathematics as we're going through this problem. So let's look at our example. It's reported that the national average credit card debt is $3,262. A college believes that their students have less credit card debt than the national average. They would like to, say, make this claim, put it in their marketing material and so on, but they don't want to just make flippant claims. Their competitors could call them on it, number one. And number two, we probably, just for our own ethics, we want to make sure that if we're saying something, that it's reasonably true. So the college collects a sample. They obtain the following sample data. Sample of size 50, X bar observed of 2995, and standard deviation of 1100. And we'll assume that that's the population standard deviation, and we know that somehow. Just like for confidence intervals, we're going to start with this simpler setup where we know the population standard deviation. And then later on, we'll look at what happens if we relax that. And we have to estimate this by the sample standard deviation. So at first glance, we might just naively say, oh, our sample mean X bar observed, 2995, is indeed less than 3262. Well, we're good. We can just make the claim, right? Well, we're not all that certain, right? Because this 2995, it could be it could be a point estimate that's really right on top of the true mean credit card debt for our students, and it could really be indicative of something systemically of our students' debt being systemically less than this 3262 national average. That could be the case. But it could also be the case that, I mean, this looks like a pretty large standard deviation. We could have a student population whose mean credit card debt is 3262 or even 33 or 3400, and maybe we just happen to get lucky. Maybe we just happen to choose 50 students who happen to have kind of overall a little lower credit card debt than our student body typically has. And we just got lucky with this number. And it's not actually all that great of evidence that our students' mean credit card debt is truly less than the national average. How do we know which one it is? Do we think this just occurred by sampling error, by chance statistics, as the narrative kind of said? Or do I think that this 29.95 is so far below 32.62 in some sense that it's unlikely to have just occurred by sampling error? So our question is, at the 5% level of significance, can the college make the claim? In other words, does this sample represent statistically significant evidence in favor of the claim that the college body credit card debt is less than the national average 32.62? This is the question we're trying to answer. If I can select it here. There we go. Let me shuffle my papers for a second here. There we go. All right, so let's set up our hypotheses. Now we have to decide what's the null hypothesis and what's the alternative hypothesis. Which one gets the benefit of the doubt and which one do we have to provide evidence in favor of in order to proceed forward with that? And typically, we set as the alternative hypothesis the thing we're trying to prove, the thing we're trying to demonstrate. So here we're trying to make a claim about mu, our student body's true mean credit card debt. And I'm trying to argue that mu is less than 32.62. That's the claim that I want to make. That's the claim that I'm collecting the sample in order to provide evidence in favor of. So then what's my null hypothesis? Well, I would like my hypotheses to be mutually exclusive. In other words, I don't want there to be any possible true value for mu that is in both H0 and H1. I don't want there to be any overlap between them. I also would like them to be exhaustive. Now, the way that we're going to write our hypotheses in a little bit here makes it look like they're not exhaustive, but we're actually going to argue that even though it doesn't look that way, it really is still exhaustive. What do I mean by exhaustive? I mean that any possible mu falls into at least one of these two hypotheses. So if I think of the real line, I want say H1 is all of the means strictly less than 32.62. And then H0 has to be all the means bigger than or equal to 32.62. If I made H0 mu bigger than or equal to 4,000, then there's a whole bunch of means that kind of fall into no man's land that I don't really know which worldview I should adopt, even if I had perfect information. And if they overlap, if H1 was mu less than 32.62 and H0 was mu bigger than 3,000, then there's a bunch of means that it's like, well, if I think that mu is 3,100, well, it's kind of both worldviews. Which one do I go with? So here I'm going to take mu bigger than or equal to 32.62. Again, we're going to revise the way that we choose to write this a tiny bit, a little bit later on, but for now, we're going to leave it this way. So these are my hypotheses. I have one worldview, the null hypothesis that the mean is bigger than or equal to 32.62, essentially that our student body looks like all of the other student bodies that this national average was taken from. And the alternative, the thing that we want to provide evidence in favor of so that we can argue for it, we can make the claim, is that the mean is less than 32.62, that the mean for our students. So here mu is our students' average credit card debt. Or our students being whatever whatever college it is. Okay, so how did my narrative go? I said, well, if the true mean number of days off was still 6.3 like it was before, then how, under that assumption, how unlikely would it be for me to get such evidence that they had gotten in the sample? Or up here, if the person was still truly innocent under the assumption of innocence, how unlikely would it be for all of this evidence against the person presented at trial to exist just kind of by chance? Or in other words, we say something like, if H naught is true, how unlikely is the sample? That's more or less what we're going to ask next. If the sample would be very unlikely if H naught is true, and more likely under H1, then we reject H naught in favor of H1. If the sample is not very unlikely under H naught, whether or not it would be more likely under H1 is irrelevant. If it's not unlikely under H naught, then we don't reject H naught. So that's our decision criterion. Our decision criterion has to do with how unlikely the sample is under the null. So anytime we're doing hypothesis testing calculations, we start with an assumption. We make an assumption, we assume H naught is true. And then I want to ask, what if, under the assumption H naught is true, what if I were to reject the null on the basis of this sample? That would be an error. How likely would it be for me to make an error where I reject the true null for a sample like this? If I assume H naught is true, then what does that mean? That means that mu bigger than or equal to 3262. Well, I have some sample data related to X bar. But hey, I know the distribution of X bar from the central limit theorem. So I know that X bar, the random variable, is normal with mu X bar equals some number mu that we're saying is bigger than or equal to 3262. And some sigma X bar that we can calculate, sigma over root n. Now mu is bigger than 3262, bigger than or equal to 3262. X bar observed is 2995. Let me put that down here. Now, if I were to reject the null in favor of the alternative for this type of a sample, if I were to argue that an X bar observed in this context of 2995 is enough evidence, is strong enough evidence to overturn the null in favor of the alternative and argue that the mean is less than 3262, I would also make that same decision at 2994, right? If X bar observed was even further to the left, 2994, that would be even stronger evidence against the null, even stronger evidence in favor of the alternative. Or 2993 or 2990 or 2900, or if I was going to reject the null at 2995, I would reject anywhere further to the left. We call this a left tail test. And that left tail has to do with this alternative hypothesis having a mu less than number, right? X bar observed values to the left of 2995 are stronger evidence against the null in favor of the alternative. So if I were to reject the null at or on the basis of this sample, I would also reject the null on the basis of any similar sample with a smaller X bar observed. But what does this area here represent? This area here represents the chance that I reject a truly false null. Or I'm sorry, I said it wrong. It's this area represents the probability that I reject a true null. I think I said a truly false null. It's the probability that I reject a true null, that I falsely reject a true null is what I intended to say. That H naught is true, but I reject it anyway. That's this probability. That's an error. That's the probability of a type 1 error. I don't want this probability to be big, right? I want this probability to be small in order to generate a rejection. If I reject for this sample, then I make an error 70% of the time. I probably ought not reject then. If I were to say if I reject on the basis of a sample, I only make an error 1 time in 1,000, like in the narrative, then I'm probably comfortable with rejecting the null in favor of the alternative. So this is the probability I reject a true null, or it's the probability that X bar, the random variable, is less than 2995. We have a name for this. We call this the p-value. So that's an important idea. We can compute the p-value, and then we say if small, or particularly if small enough, then we reject H naught. Otherwise, do not reject H naught. So how do I compute a p-value? Well, in theory, it's not hard. I just have a normal distribution question. The probability that a normally distributed random variable is to the left of 2995, that's not bad. I do have an issue, though. X bar is centered at mu, but mu is just some number bigger than or equal to 3262. I mean, mu could be like equal to 3262, and maybe I get a picture like this. If mu was like 3400, I would get a similar picture shifted to the right. Or if it was, 4,000, I'd get a similar picture shifted even further to the right. Which mu should I pick? Well, if I'm going to give the benefit of the doubt to the null, if I'm going to give it the benefit of the doubt, if I'm going to set the bar really high, if I'm going to demand quite strong evidence from my sample in order to overturn the null in favor of the alternative and make the statement that I'm already kind of biased towards, that I'm already wanting to make, if I'm going to demand a high level of evidence, I should be able to reject against any mu bigger than or equal to 3262. I should pick the most conservative estimate, the mu that's hardest to reject against. Well, what I notice is that the larger mu gets, actually the smaller this left tail gets, right? If I push my mu from 3262 to 3400 or 4000, this area in the tail over here gets smaller and smaller and smaller because my mean gets further and further away from my X bar observed. That pushes it further in the tail, that makes the area smaller. So it's easier for me to reject against larger means in this case. So I'm going to choose to test against the mean that's right at that border, right at that boundary line. I'm going to choose to test against mu equals 3262. This one right here. If I can reject against that one that's super close to my alternative hypothesis region, if I reject there, if I can reject the null in favor of the alternative there, and I'm confident doing that, if the true mean was even higher than that, then I could reject even more easily, or with even more certainty, or however you want to put it. So because of this, because we're always testing against the mean that's right at that boundary, quite often in our statement of the hypotheses, we don't actually write greater than or equal to. Quite often we just write equals, because that's really what we're testing against. But this kind of encompasses all of the mu's bigger than or equal to 3262. This is the most conservative choice for the null. It's the one that if I can reject against this one, I can reject against any other mu that you might throw out there that's bigger than 3262 as well. Okay, so now we've nailed everything down enough that we can actually do this computation. We need one more little detail. We need to figure out what sigma x bar is. We'll just come back to that. And sigma x bar is, of course, sigma over root n, 1100 over root 50. And now we need the calculator. Let me switch my share back over. And this gives me about 156. And remember that I'm choosing to center my distribution down here under this assumption that H naught is true. I'm choosing to center it around 3262. The most conservative choice for mu, the one that if I can reject against a mu of 3262, I can reject against any other mu that might be in that original null hypothesis. Well, okay, I think I have enough to answer this now. My p-value is the probability x bar less than 2995, but that's the probability that z is less than the x index, or the x bar index, minus its mean, 3262, over its standard error of about 156. That's the probability z is less than, let's see what that is. It's about negative 1.71. So this is about a 1.7 standard deviation event. I think we have a gut feeling that it's not super unlikely. Let's look carefully, though, at our normal table and find the area to the left of negative 1.71. Here's the area to the left of negative 1.701, or that's 4.36%. So my p-value, the probability of making a type 1 error if I reject based on this sample, my kind of, in a sense, observed or empirical error rate would be 4.36% approximately. Now the question I have to ask is, or an answer is this error rate small enough? Am I unlikely enough to generate an error in this direction that I'm willing to reject the null in favor of the alternative? Or is this too large an error rate? Is this 4.36% too high? Do I say that's too much of a chance of making an error and I'm not willing to reject? And I would fail to reject H naught, and I'd fail to reject H naught, and I would continue forward under the null. There's one piece of information we haven't used yet, and that is this statement here at the 5% level of significance. So alpha is 5%. It's the maximum allowable type 1 error rate to generate a rejection. There's no, in a sense, good reason that alpha is 5% in this problem, or 1% in another problem, or 10% in a different problem. This is something that somebody has to choose, right? It has to be chosen subject to this trade-off. We could make alpha smaller, 1%, but that comes at the cost of a higher beta, a higher type 2 error. Or we could make alpha larger if we want to achieve a smaller type 2 error. It does turn out, though, that if you look in the literature, in almost all medical literature, 5% is like almost universally used. In finance literature, quite often, they do something a little more complicated where they basically run every hypothesis test at the 1%, 5%, and 10% level, and then report all three numbers. So it kind of depends on the field what the standard is, but in the medical field anyway, 5% is like the standard that everybody kind of agrees on. So why are we using 5% here? Well, you know, the most straightforward answer is because we picked it and that's what it is. It's a part of the problem, the same way that why are we talking about national average credit card debt? It's because that's part of the problem. But why would a person choose to use 5% instead of 10 or 1 or 7.3%? And the answer is basically that's what other folks in their field are using. Yeah, question? Okay. Yeah, so why would somebody, in a broader sense, choose 5% as opposed to something else? Basically, that's the standard in the field for a lot of fields. So a lot of our problems will use the 5% level, just because it's such a widely used standard. I don't think there's particularly a really, really good reason for that, other than the fact that everybody uses it. So everybody kind of intuitively understands the interpretation and can compare apples to apples. And because everybody uses it, everybody continues to use it. So it's a strong status quo bias. So we did all of this work. We said if H naught is true, and if we reject on the basis of this sample, if I say that I think this sample represents strong enough evidence to reject the null in favor of the alternative, then I would make an error because I would reject a true null. If I reject for X bar observed 2995, I would reject for any X bar observed further to the left. And the probability that if the null was true, in the most conservative case, that I would get a sample mean to the left of 2995 for a sample of this type with this sample size and standard deviation and so on. The probability that I would get a sample in that region, the probability that I would falsely reject a true null, I think I said it right that time, is the p-value. That is 4.36%. That is our observed error rate if I were to reject on the basis of this sample. My maximum allowable error rate is 5%. And now we can say, since the actual observed error rate, if we were to reject, the p-value is 4.36%, and that's less error than 5%, the maximum allowable error rate, since p is less than alpha. Since if we reject, we make an error less amount of the time than the maximum allowable, then we reject H naught in favor of H1, and we can make the claim. Or another way of saying this, we can say that this sample, the sample size 50 with a mean of 2995 and a known standard deviation 1100, provides statistically significant evidence in favor of H1, and we might append at the 5% level if we wanted to be to give a little more detail. So we could say the sample provides statistically significant evidence in favor of our claim or in favor of the alternative hypothesis. Or we could simply say, because P is less than alpha, we reject H naught in favor of H1, we can make the claim. So this sample by itself, just looking at these three numbers, isn't really enough for us to make the claim. We can't just say, because X bar observed is less than the mean we're testing against, we can make the claim, because that could have occurred by sampling error. What we've shown here is that it's sufficiently unlikely for that to have just occurred by sampling error that we should feel confident making the claim, and that it's not likely to be just sampling error at play here. There's likely to be something systematic at play here. Now, have we proven that the mean is 2995 or super close to 2995, or that it's way less than 3262? No, we haven't. It might be like 3261 or something. We've just provided statistically significant evidence that the mean is less than 3262, that our students have less credit card debt than the national average. Now, from chapter 7, if you asked me, what's my best guess at what the mean is, I would answer 2995. If you ask me what's a 95% confidence interval, I would use this sample to build a 95% confidence interval, right? So we can answer those questions from chapter 7, and they're very parallel questions to the one we answered here. Are there any questions so far? Okay, so I answered this one way. I answered this with the p-value way, where I computed the probability of a type 1 error under the assumption that H naught is true, the probability that we would see a sample like this or more extreme. We could take a second approach. And the second approach is sometimes the way to go. The first approach is sometimes the way to go. So we have method 1. P-value. We could take a second approach that's sometimes more useful. We have another method we could use called the rejection region method. Now, I want to be clear. What we did above completely and fully answered this question. We did this work, we got to this black box here, we're done, we answered the question. But in a different question or whatever, we might want to use a different method to get that same answer. So that's what we're looking at here. We're looking at a second way that we could have solved this problem. We don't need to, for each problem, do both methods. Typically, we do one method, but we would choose the method that kind of works best for the context of that problem. One thing that I see is nice about method 1, the p-value method. Well, remember when I said, like in finance and economics journals, quite often they will run the numbers 3 times in a sense, where they'll look at the 1% level of significance, the 5% level, and the 10% level, and they'll report all 3 of them. Well, that's actually super easy to do here. Since I computed my p-value, and remember, I didn't use anything about this 5% level of significance. I didn't look at that 5% number at all until I was all the way down here. All of these calculations that I did that took quite a while to set up and to perform and all of that, all of these, and again, this goes a lot faster when you're not building the method as you're going through it. So don't think every time you do one of these problems is going to take a half an hour. But I got all the way down to here before looking at alpha at all. And then my very last step was just comparing the p-value to alpha. So I can ask really easily, what if alpha was 10%? Can I generate a rejection? Well, my p-value is 4.36%, which is indeed less than 10%. So we reject H naught at the 10% level as well. And I squeeze my rejection region headline in there a little too tight, but hopefully this will just move. There we go. Good. I could ask the other question, what about alpha equals 1%? If instead somebody had chosen alpha equals 1%, could I reject at the 1% level on the basis of this same sample and this same setup? Well, here P is 4.36%. Is that less than 1%? No, it's not less than 1%. The actual error rate, the actual type 1 error rate, if I rejected under the sample, would be a little over 4%. But if alpha was 1%, if that had been chosen instead as my level of significance, the maximum allowable error rate would be 1%. The achieved error rate would be 4%. That's too much error to reject. Do not reject H naught at the 1% level. If I compute a p-value, I can tell just at a quick glance, you give me a significance level, I can tell you right away whether to reject or not. That's a benefit of the p-value method. I can test against several different significance levels, 1, 5, and 10%, let's say, very quickly without any additional work. I mean, with trivial additional work, just is it less than or not? So that's a benefit of the p-value method. There is a cost of the p-value method, though. What if I'm a college, whatever, credit card debt consultant, I don't know, and I go around to a bunch of different colleges and take very similar samples. One college, I get $29.95, I go through, I compute my p-value, I do all this work. I say, okay, good, at $29.95, I can reject at the 5% level. Nice. I go to the next college and I do the same setup, the same sample of size 50 with standard deviation of 1100 known, but unfortunately that college, my X bar observed is 29.97. Can I still reject? Well, I don't know. I have to actually do all of this work all over again, replacing 29.95 with 29.97, figure out a completely different p-value. It's going to be a little bit higher, but it's going to be closer to 5%. Is it over 5%? I'm not sure. I have to do all the work all over again when I get a different X bar observed to say what my p-value is and then to assess whether I can reject. Wouldn't it be nice if I said, what's the borderline X bar observed? What's the cutoff where I say, for a setup like this, sample of size 50, standard deviation 1100, 5% level of significance, what's the borderline X bar observed where I can say, if your X bar observed under this setup is less than this number, yes, you can reject. If it's not less than this number, no, you cannot reject. Then I can go around to each college and just look at my X bar observed and compare it to that number and right away tell whether I could reject or not. So if I have a bunch of different samples, I might run a rejection region method rather than using a p-value method, because then I just have to remember one number, whatever that cutoff number is, and just look at what side X bar observed ends up on. It's a little bit of a silly example here, but you can imagine if you were a quality control engineer in a big plant and you have 10 very similar machines working, 24/7, and 3 times a day, you're going to take a sample of size 50 from one of the machines and get an X bar observed and so on. It would be nice to not have to do this, 10 times a day for each of those 10 machines or whatever it may be. It would be really nice to just have one number that you can keep on a slip of paper in your pocket or something. And when you get your X bar observed for each machine, you just look at it and you say, okay, it's to the left, shut the machine down. It's not to the left, this machine can keep running. Right. So there are situations where this makes a little more sense than my kind of college credit card debt situation here. And we'll actually see one of those in the next example, but we're going to work through it here though. So just like up above, we always start our calculations in hypothesis testing with assuming H naught is true. We give the benefit of the doubt there. It gets the kind of status quo bias. It gets to be the default assumption. And remember that now we're thinking of H naught as just being mu equals 3262. It's kind of the most conservative mu that we can pick from the mu's bigger than or equal to 3262. It's the hardest one to reject against. If we can reject against this mu, we could reject against any other mu bigger than 3262. I would like to find an X bar observed. I would like to find a cutoff. Maybe I'll call it L because it's kind of a lower bound in a sense. So this is a cutoff, X bar observed equals L, such that my p-value for this is right at 5%. And just like before, this is X bar, the random variable is normal with mean 3262 and standard deviation was at 156, I think. Yeah. Standard deviation 156. So this is the borderline X bar observed, where if the actual X bar observed I find in my sample is to the left of L, then I know that my p-value has to be less than 5% because this is the one that gives you 5% area to the left. And if my X bar observed was to the left of that, it's going to cut off a little bit of that area. My p-value will be a bit less than 5%. So I'm looking for the L that gives me an area to the left of alpha, the significance level. So I'm looking for probability X bar observed less than L equals 5%. In other words, I'm looking for the 5th percentile of this distribution. Why did I choose 5%? Because that's alpha. Here I build alpha in from the very beginning, right? The previous way, I didn't use alpha at all until the very end. Here I'm using alpha at the very beginning. If I wanted to change alpha, I would have to rework all of the work that I'm about to do. But here I know that P 5%, in other words, the probability Z less than, or P5, not P5%, is the right notation. Probability Z less than P5 equals 5%, the fifth percentile of the Z distribution. What is that? The 5th percentile of the Z distribution is negative 1.645. But I also know that Z equals X minus mu over sigma, or that X equals mu plus Z sigma. So if I want to find my associated X index or my L, it's going to be the mean of the distribution 3262 plus Z. The associated Z index is negative 1.645 times the standard deviation of this distribution, 156. This should all look familiar from chapter 6 and chapter 7. And I can figure out what is 3262 minus 1.645 times 156. That looks right. That's 3005. Let's just call it 3005. So I have a lower bound of 3005, and this is a left tail test. X bar observes farther to the left provide stronger evidence against H naught and in favor of H1. Again, because H1 has a less than sign. If I had X bar observed way off to the right, that wouldn't be evidence at all that mu is less than 3262. So what's my decision criterion here? If X bar observed is to the left of 3005, we reject H naught in favor of H1. Otherwise, if X bar observed bigger than or equal to 3005, do not reject. And now we can look at our actual sample. So now the thing that we're using very last is our X bar observed from the sample, 2995. And here we can say, since X bar observed is 2995, which is less than 3005, it is in the rejection region, which is what we call this area to the left of L in this case. Since it's in the rejection region, we reject H naught in favor of H1. We provide a statistically significant evidence in favor of our claim. Again, the benefit of going this route is if I go to a different school with the same setup with sample size and everything, and I get my X bar observed 2997, it's less than 3005, I can reject. If I get 2990, it's less than 3005, I can reject. If I get 3020, not less than 3005, I cannot reject. But if I wanted to ask the same question about a different alpha, well, when I switch alpha to 1% or 10% or whatever, I have to rework all of this because this number will change. All right, so that finishes us up for today. Let me stop the recording.